we get to talk about some boring information today. Boring as in B-O-H-R-I-N-G. Boring as in Niels Bohr, the gentleman on the right, having so much fun apparently watching a coin roll on the floor. Now, who can say he's boring? In October of 2012, last year, the Google logo on one day was this, in commemoration of Dr. Bohr's birthday. And what we want to be able to do is to understand this logo by the end of this little video. What does this n equals 2, n equals 3, n equals 1 mean? What is this thing with the arrow coming out of it? What are these jagged lines and this equation? Hopefully, if you pay close attention, by the end of this video, you will know. Bohr worked with the hydrogen atom. Hydrogen was a common substance, as you well know. Hydrogen is the most common element in the universe. In this beautiful picture of the Tarantula Nebula, hydrogen is the red gas. Bohr worked with the hydrogen atom because it was very simple. It has a single proton in the nucleus. Remember, H1, the first isotope of hydrogen, hydrogen 1, has no neutrons, just a proton in the nucleus. And it has a single electron outside of the nucleus of the atom. Now, prior to Bohr's time, there was a lot of controversy. There was a lot of unease about what that electron, why it did not fall into that positive nucleus. Bohr helped answer some of those questions. And he did that by studying the spectral lines of hydrogen. He saw that hydrogen gave off only certain colors. He saw that it was not a continuous spectrum. Why were there these discrete, separate lines? And why didn't those electrons spiral into the nucleus? To understand the answer to these questions, you have to understand the electromagnetic spectrum, which is this series of all the electromagnetic waves, ordered according to wavelength and frequency. So we have things like radio waves, which have a very long wavelength, microwaves a little bit shorter, infrared shorter, visible light. Look at visible light. We use it so much and we're so used to it, but it's only a very narrow range of the electromagnetic spectrum. Then you get even shorter waves up to gamma rays. But notice the frequency of these waves is inversely related to the wavelength. So you have a very long wavelength, but you have a very low frequency. You have a very short wavelength, you have a very high frequency. And then this is what's becoming very important, the energy of a photon. Now, photon is a particle of light. And the energy in that particle of light can be expressed from this equation over here, E equals hf. H standing for Planck's constant. F, I'm using frequency. That is not the quite correct annotation for that. The correct notation should really be energy equals Planck's constant times nu. This is the symbol for frequency in physics. It's a Greek letter of the alphabet called nu. It means the same thing as frequency. So since frequency is a little bit clearer, I'm going to use F for frequency. Now you see on this electromagnetic spectrum, as the wavelength gets shorter, the frequency gets higher, and there's more energy in that light wave. Well, Bohr proposed that perhaps electrons are giving off energy when they jump from higher energy states to lower energy states. So Bohr envisioned this hydrogen atom as having the nucleus here, and it had these different energy states or energy shells around it. And he labeled those as n equals 1, n equals 2, n equals 3, n equals 4, all the way up to n equals 7. So there's 7 energy states. That should sound a little familiar to you. If an electron was up here, it was unstable. It was at a high energy state and it immediately wanted to jump back down to a lower energy state. And when it jumped back down, it emitted a photon of light, a particle of light, equal to the energy in that wavelength of light according to Planck's equation. E equals Planck's constant times the frequency of the light. And as you can see on this diagram, we have 3 series of spectral lines for hydrogen: the Lyman, Balmer, and the Paschen. Lyman series go back down to n equals 1. This is this spectral line series is in the ultraviolet range. We do not see them with our eyes. The Balmer series we do see. This is in the visible light range. And the Paschen series, the electrons jump from higher energy levels down to n equals 3. This is lower energy photons. This is in the infrared series. Here's another diagram expressing the same thing. We have the high energy levels here, 7, okay? And we can go back down to n equals 1. This would be the Lyman series again in the ultraviolet range, going back down to n equals 1. Here the electrons are jumping down to n equals 2. That's the Balmer series, and then the n equals 3. The electrons are jumping back down in the Paschen series. Now, when the electrons are back down to their lowest energy state possible, or start at their lowest energy state possible, we say they are in their ground state. When they absorb energy to jump to higher energy levels, then we say they are excited electrons. Okay, they're not in their ground state, or we can think of that as their normal state. I'm going to show you an animation which might make this a little bit clearer for you. Just remember, a photon is a packet of light. It has a certain amount of energy in it, a particle of light, according to Planck's equation. Watch what happens when a photon is absorbed. Watch what happens when a photon is released. And then think about why electrons do not go halfway between the energy levels. So here we have our little model. I hope you can see the energy levels on there. And we'll watch this for 30 seconds or so. Here comes a photon, hits the electron jumps up. Electron jumps back down, gives off an equivalent photon of light. Notice in that first, when it jumps up 1, it's absorbing red light, emits red light when it jumps back down. Let's give it a photon with a little bit more energy and see what happens. Comes in, wow, now it jumps up 4, 5 energy levels, 1, 2, 3, 4, 5 energy levels, and then it jumps back down, but not all at once. It jumps down in a few different steps. And here, when it's jumping back down in those few different steps, you can see the spectral lines of hydrogen. Oh, there it jumped back down in one step. Let's watch it again. Okay, so some spectral lines of hydrogen there. Well, why didn't the electrons go halfway? Because they could not go halfway. Energy is quantized. It comes in packets. You either absorb a packet of light energy or you don't. If you absorb it, you can jump up one energy state, one energy level, but you can't go halfway in between. It's like walking up steps. You go up 1 step or 2 steps or 3 steps, but you can't go up a half a step, okay? And so the same thing with these electrons, and the energy is quantized. So Bohr did some very interesting work, although we can still say it was boring work because he did it. He came up with this idea of energy levels. He came up with this idea that electrons can become excited. They can absorb energy and jump up energy levels. They then immediately will jump back down to lower energy levels, and in the process give off discrete quanta of energy, which shows up as the spectral lines. And the energy that we can calculate the energy in each jump by the color it gives of light it gives off, and Planck's equation, energy equals Planck's constant times the frequency of that energy. So now when we go back to look at this Google logo, you can be one of the people that understand what this logo is all about, that the n equals 2, the n equals 3, the n equals 1 are energy states of electrons, that this here is the nucleus, and that this is an electron and it's jumping back down. And I know it's jumping back down because it's emitting a wavelength of light, and the wavelength of light is given by Planck's equation, E equals Planck's constant times the frequency of the light. Now the cool thing is, these energy levels are called the first quantum number, the symbol of which is n. And this is a very useful and interesting to you, because we can now discuss electron configuration and bonding.